Any questions? Okay, so if you remember, on Monday we were kind of looking at this funny integral. We were considering such transition amplitudes, let's say a particle at the point x1 at the time t1. What is the amplitude that at the time, let's say tn, it will be at the point xn. So it starts at t1 at the point x1, and at a later time it will be at the point xn. And we said that we can write this as an integral of the form m over 2 pi I h bar delta t, putting all the factors, n minus 1 over 2, dx2, dx3, dxn minus 2, times e to the power I over h bar, s being the action for this path. And in the continuum limit, we basically denote this by, when we take the limit as delta t goes to 0, this just becomes, we use this funny notation. Here we have the Lagrangian, the classical Lagrangian. There are no operators left anymore. Everything is what we have in classical physics. Of course, the classical Lagrangian depends on this position at the time t and the velocity at the time t from t1 up to t2. And this classical path has the boundary condition that at x t equal to t1, it should start from x1, and when t is equal to tn, it should end at tn. And the basic idea we had used here was the amplitude for a particle to go from here to there, let's say, is basically first to go here, and then to go here, here, and you basically divide your time interval into various steps. This is at t1, this is at tn, this is t2, this is t3, here you have ti, the final time is tn. So the particle should be somewhere at the time t2, and then somewhere else at the time t3, t4, etc. And eventually you reach your final destination. And in the interval at t2, t3, t4, basically we don't know where it is. It can be anywhere. So that's why we have here the integrals over all the intermediate positions at x2, x3, etc. So this, in a sense, this approach, at least in a sense, just brings back the idea of the trajectory of the particle back into quantum physics. Of course, there is not a single trajectory that the particle can follow. The particle can follow any trajectory, not subject to any laws, let's say. It can follow any trajectory, but every trajectory has a contribution. The contribution of every trajectory, it contributes some amount to the amplitude, and that contribution is given by the action corresponding to that path. And here, this is just kind of a short notation for the same thing. Now, today I would like to do a simple example of one problem that we had already studied. We had already calculated this matrix element, or so-called the propagator, for a free particle. Now we can do the same thing for the path integral. Well, it is more cumbersome than just straightforward calculation of the propagator. So I'm not going to claim that path integral formalism is easier than the Schrödinger formalism, at least for the simple problems, like the free particle or the harmonic oscillator. But nevertheless, I mean, there are some advantages. Certain things that would be difficult to show in Schrödinger picture just come out naturally in the path integral formalism, and that is something we will be using in our following discussions about various phenomena. So that's why I still want to do one example at least of how to calculate this path integral. Now, any questions? Because we know that once we evaluate this quantity, now the point is that once we evaluate this quantity, we already know that we can evaluate the time evolution of any operator. We know how to calculate, we had discussed how to calculate the eigenfunctions for our system and the corresponding eigenvalues just from the knowledge of this quantity over here. So in a sense, knowing this parameter gives us a description equivalent to the Schrödinger equation description of quantum dynamics. It encodes all the dynamics in our problem. Now let me write down the, well, you see, if you look at this integral, S is basically an integral, but we can also write S as a summation over times delta t. Now these time intervals are separated by delta t. S is by delta t, sum over I, S of ti and ti minus 1, the action between those two times. And this S ti and ti minus 1, we had calculated it to be just for the free particle, it's just xi minus xi minus 1 squared divided by, we have 1 over 2 m delta t squared. This is what our action is. So let me consider this integral. I am integrating over xi. It will be from minus infinity to plus infinity. You see, if you look at the expression for the path integral, I'm just integrating over all the possible values of xi. Then inside I have the e to the power exponential of I over h bar. Well, S is just sum of all the contributions from each one of these small time intervals. But among these sum, S is just that sum over there. Among that sum, the only terms that contain xi would be just S of ti plus 1, ti minus S of ti and ti minus 1. Only these two terms plus contain the position xi. The other terms do not contain the position xi. Remember, xi is just x at ti. So all the other terms in my integrals over here, they are independent of xi. So let us just write it out explicitly. The xi exponential of I over h bar. Well, just using the definition of S, of course here I also have delta t. And then here I have all of them contain 1 over 2 m. The first is xi plus 1 minus xi squared divided by delta t squared plus xi minus 1 squared divided by delta t squared. Let me just reorganize them a bit. From minus infinity to infinity, the xi exponential of I 1 over, no, I m over 2 h bar 1 over delta t. Well, this cancels one of these delta t's. What is left inside will be xi squared minus twice xi plus 1 minus xi minus 1 plus xi plus 1 squared plus xi minus 1 squared. I just opened up those parentheses. Well, let me just complete it to squares. I will just add xi plus 1 minus xi minus 1 squared and subtract the same thing. So that the integral is just the xi exponential of im divided by 2 h bar delta t. Xi minus xi plus 1 minus xi minus 1 squared. Sorry, this is a plus sign over here. I had a mistake above. All of this squared. It is just these three terms over here. They just give me that square. And then I have plus xi plus 1 squared plus xi minus 1 squared minus xi plus 1 plus xi minus 1 squared. So I have another mistake over here. There is a 2 over here, which I forgot. You see, each one of those terms bring a factor of 2xi, and from each one I have minus 2xi times xi plus 1 and minus 2xi times xi minus 1. So what I will be adding here is plus 2 times 1 over 4. Now, why I wrote it that way, 2 is just the common in xi squared. That is what I will be factoring out. And 1 over 4 is just so that I have this complete square over here. So this will be twice. Here I have 1 over 2. And then here I have minus 1 over 2. So if you just open up the parentheses, you will see that I recover my previous result. Now you see, what I gain by this deal, let's say, is that now let me define another variable yi, which will be just xi minus 1 over 2, xi plus 1 plus xi minus 1. So in terms of this new variable, my integral is just integral over yi. Instead of xi, now I'm integrating over yi. Exponential of im over 2 h bar delta t times twice yi squared plus 1 over 2 xi plus 1 minus xi minus 1 squared. No, minus 1 over 2. No, plus. You see, if you open up that square in the second line, there I get a xi plus 1 squared with a minus 1 half. You see over here, I have with a minus 1 half xi plus 1 squared. I have another xi plus 1 squared, so at the end I end up having 1 over 2 xi plus 1 squared, which is over here the square of this one. The same thing for xi minus 1, so it's the square of this one. Then I have the cross term minus plus twice xi minus 1 times xi plus 1 over here, but then I have a minus 1 over 2, so that gives me a minus 1 xi minus 1. If you look at over here, if you take the square, it's just the product of these two with minus 2, then I divide by 2, so I end up having minus 1. So this square over here is just these three terms. But this is just like a Gaussian integral, the yi integral, with alpha being minus I m over h bar delta t. So the yi integral just becomes square root of pi over alpha times exponential of im over 2 4h bar delta t times xi plus 1 minus xi minus 1 squared. Or let me also write this in the form 2 times 2. Now I will explain why I wrote it that way. This is square root of pi I h bar delta t over m. I just put in the value of alpha. Exponential of I over h bar, well, I over 2h bar, times delta t, times 1 over 2 m xi plus 1 minus xi minus 1 squared divided by delta t squared. Well, you see, if you look at this factor over here, you see what we started with. We started with, if you look at the above part of the screen, we started with that integral we had on that first line over there. We had two velocity squares. Now, taking the integral of the coordinate in the middle between xi minus 1 and xi plus 2, I almost obtain exactly the same expression. Almost exactly the same expression. Just that ignore, it's just, if you omit the xi term and just jump from xi plus 1 to xi minus 1, you would get exactly this expression. The differences, I have this additional factor and this factor 2. Those are basically the only differences I have. So let me just take one more integral. Let me also evaluate the xi plus 1 integral. You see, here I have evaluated one of the integrals. I have infinitely many of them. So there's no point in there's no hope that I will be able to evaluate all of them one by one. But if I can see some kind of a pattern, then I can just generalize it to arbitrary number of integrals. So that's what I will be trying to do. There's already seems to be some kind of a pattern in it. You see, just evaluating one integral brings me that prefactor over there, and the overall coefficient, the h bar, just becomes 2h bar. My guess will be, if I evaluate one more integral, that 2 will become 3. And then one more integral, 3 will become 4. N integrals, that 2 will just become n. So then I know how to evaluate my expression for a general n, and then take the limit as the number of integration variables is infinite. That is what I will try to see. And also look at that prefactor over there. I have 2 pi h bar delta t over m. Now if you look at our definition of the full matrix element, I have m over h bar delta t's over there. Here I get h bar delta t over m's over there. This 1/2 is multiplying everything. Well, that is also kind of nice, because eventually I will take the limit as delta t goes to 0. I should get rid of them somehow. But those prefactors are basically exactly canceling those delta t's in the prefactor. So let's just proceed and evaluate one more integral, and then we will basically see the pattern. So before, what I evaluated was the xi. Now let me evaluate from minus infinity to infinity the xi from minus infinity to infinity dxi plus 1 exponential of I over h bar s of I plus 2, I plus 1, s of I plus 1, I plus s of I minus 1. Now I had already evaluated the xi integral, so I will just write the result. This is dxi plus 1 from minus infinity to infinity I pi h bar delta t over m to the power 1 half exponential of I over h bar 1 over 2 m xi plus 2 minus xi plus 1 divided by delta t squared. This is the first term. I didn't do anything with it. The other two s's, I had integrated over them, and the result is just I over twice h bar. Well, let me just put some number n over here to see whether it will be just n plus 1 or twice n or what I want. We will see. Times delta t well, let me just move them below. 1 over 2 m xi plus 1 minus xi minus 1 squared over delta t squared. So this is what I need to evaluate now. This is equal to, from minus infinity to infinity, dxi plus 1 I pi h bar delta t over m to the power 1 half exponential. Well, let me just try to combine some of those, just factor out some of the common factors. Both of those terms have I over h bar. They have delta t, they have 1 over m, they have 1 over delta t squared also. And I will also factor out 1 over n. What remains inside? Well, from the first term I have n times xi plus 2 minus xi plus 1 squared. That is the first term. The other term, I factor out all the prefactors, and only the square remains. Now I will basically do the same trick. I will just complete the squares with respect to xi plus 1, evaluate the Gaussian integral, and I will obtain an expression that contains only xi plus 2 and xi minus 1. That will be my trick. This is equal to, well, the integral, the xi plus 1 I pi h bar delta t over m to the power 1 half exponential of I over h bar 1 over 2 m 1 over delta t 1 over n. These are all the prefactors I have. Now what remains, okay, I have n plus 1 factors of xi plus 1 squared. I have n of them from the first square and 1 from the second squared. Then I have minus twice xi plus 1 n times xi plus 2 minus x plus xi minus 1. These are the mixed terms in both of those squared terms. And then I have plus xi plus 1 squared n times plus xi minus 1 squared. These are all the terms I have. Now here what I will add n plus 1 times n xi plus 2 plus xi minus 1 squared divided by n plus 1 squared So that those three terms, when I factor out the n plus 1, what remains will be just a square, a complete square. And since I'm adding that, I have to subtract that also. Okay, so this is what I have in the exponent. I just added and subtracted the same thing. Let me just reorganize it slightly. N plus 1 times xi plus 1 minus n times xi plus 2 plus xi minus 1 divided by n plus 1. All of this thing squared. Now this is my Gaussian integral part. And then I have the other terms. Plus n times xi plus 1 squared plus xi minus 1 squared minus, let me take that square, n squared xi plus 2 squared plus xi minus 1 squared plus 2n xi plus 2 xi minus 1. All of this thing divided by n plus 1. Now I can take the xi plus 1 integral. That's just a Gaussian. You can, if you like, you can just call this yi. So you have the yi squared. So this is I pi h bar delta t over m to the power 1/2. Then I have pi over minus I over h bar 1 over 2 m 1 over delta t n plus 1 over n. All of this under the square root. This is just the coefficient of this yi squared, minus the coefficient of yi squared. And then what remains, well, that I need to organize a bit. Let's see, xi plus, I have all those factors. Then xi plus 1 squared, I have n minus n squared over n plus 1. The n comes from the first line of the exponent, the n squared over n plus 1 comes from the third line on the screen. You see, n is over here, n squared over n plus 1 is from here with a minus sign. Then I have xi minus 1 squared. It comes with 1 minus 1 over n plus 1. And then I have the mixed term, which is minus 2n xi plus, no, these are xi plus 2, sorry. So xi plus 1 is already over here. So xi plus 1 squared. So these are xi plus 2 squares. Xi plus 2, xi minus 1 divided by n plus 1. Now this parenthesis over here. What is that parenthesis? If you just equate the denominators. 1 over n plus 1. This one. 1 over n plus 1. N over n plus 1. Yes. This one. No, n squares cancel. You see, I have... Yes? Yeah, that's also true. N over n plus 1. Correct. So you see all of those terms are n over n plus 1. N's will cancel. I pi h bar delta t over m to the power 1/2 I pi h bar 2 n over n art n plus 1 over m times delta t to the power 1/2 exponent I over h bar 1 over 2m 1 over delta t 1 over n plus 1 xi plus 1 squared minus xi minus 1, no, plus 2. Xi plus 2 minus xi plus minus 1, all of this thing squared. So basically, now we see the pattern. You see xi minus 1, what we are evaluating here. So we have a particle that starts from x1, it goes up to xn. So here we picked up a time interval, ti. At the point ti, we say that it's at the point xi. This is the position xi minus 1. This is xi plus 1. This is, let's say, xi plus 2. Now, if we evaluate one integral, we evaluate only xi, keeping xi minus 1 there and xi plus 1, its position at the time 1 moment before and then its position at 1 moment after. The result of the integral is 1 over 2m. This is again 1 plus 1. If we evaluate one integral, that factor multiplying I over h bar, dividing I over h bar, is just 1 plus 1. And now we have here the differences of its positions, one before and one after, squared. We are evaluating one integral with that one factor of delta t over m pi h bar I, etc. Now, if we evaluate one more integral, two integrals, well, here we said we kept n kind of arbitrary, but basically n was before 1. We had one integral. Now we evaluated it twice, n is now 2. So we still have the differences of the positions, one before and one after squared. It is this square over here. We divide it by 1 over n plus 1, n being the number of integrations we had carried out. And now we have this 1 over delta t, 1 over 2 m I over h bar, etc. Now let's see how many integrals do we have. Let's go back to the definition. We are integrating from x2 up to xn minus 2. How many integrals do we have? In terms of n, we will take the n to infinity. But for the time being, n is finite. We are evaluating x2, x3, x4. We are not integrating over x1 and we are not integrating over xn, but we are integrating over all the time intervals in between. How many time intervals we have that we are integrating over? N minus 2. So if we evaluate all of them, If we evaluate all n minus 2 integrals, we obtain xn tn x1 t1, which will be exponential I over h bar 1 over 2 m 1 over delta t 1 over n minus 1 xn minus x1, because those are the positions, one after my last time integration, one after my last position integral, and one before my first time position integration, squared. Multiplied with I pi h bar delta t over m to the power 1/2, but I have n minus 1 of them, n minus 2 of them, sorry. N minus 1 of them, because every integral, n minus 2. No, n minus 2. Every integral will bring me such a factor. Then there is that 2n over n plus 1 factors. Well, you see, this factor is kind of tricky, because when I evaluate the first integral, I get 2 over 1 plus 1. When I evaluate the second integral, now n just became 2, not 1. I became 2 times 2 over 2 plus 1. Then 2 times 3 over 3 plus 1. Up to 2 times n minus 1 divided by n minus 1 plus 1. So that factor kind of changed at every step. It's not just the number of steps. But you see, in the definition of this matrix element to start with, I also have a prefactor over there. M over 2 pi I h bar delta t raised to the power n minus 1 over 2. Well, let me just move this 2 also over here. So this is 1. I don't have those 2's. 2 pi I h bar delta t m. Almost all of it is cancelled except on 1/2. You see here I have n minus 2 of them. Here I have n minus 1 over 2 of them. So what remains is minus 1 over 2. This is also cancelled. Well, you see, in these prefactors, I have 2 cancels 2, 3 cancels 3, 4 cancels 4. This will cancel this one. I have n. And this is also under the square root, sorry. But you see, I'm taking a limit. I will be taking the limit. N goes to infinity. Delta t goes to 0, such that n times delta t is equal to t n minus t1. It is fixed. So if I take that limit, my expression becomes exponential of I over h bar 1 over 2 m xn minus x1 squared divided by t2 tn minus t1. This is my exponent. Here what will remain is just m square root of m over 2 I pi h bar t2 minus t1. So this is my matrix element. Now I have evaluated infinitely many integrals. Now this is Tn minus T1. Now this was the expression that we had also derived before. It's basically the same expression. Now, I'm not going to claim that this is an easier method than solving the Schrödinger equation. But to prove certain things, this will be easier, and in some cases, especially in much more complicated problems where you cannot really write down a Schrödinger equation to solve, I mean, this might be easier to put it on the computer and let the computer solve it for you. In fact, you can, for example, derive the WKB approximation from here, so-called the semi-classical approximation. You see, here we have this path integral definition. This is the definition of the path integral. We also said that since h bar is a small number, the dominant contribution to that summation over the path will be the classical path. So I just replace the action over there with the action of the classical path. That's your first approximation. If you know the solution of the classical problem, you have an approximate solution of the quantum mechanical problem. And that approximation basically corresponds to WKB. Well, if you want, just take the harmonic fluctuations around the classical solution. So you see here we have S, X. We can just write the action, classical plus the variations from the classical path. This you can write kind of like a Fourier series, Taylor expansion, sorry, plus the derivative of S with respect to eta times eta, evaluated at x is equal to x classical, plus the second variation of S with respect to eta squared times eta squared, again evaluated at x is equal to x classical plus higher order terms. Well, this is just zero because the classical path, the variation of the action around the classical path is by definition zero. So this is your first correction from quantum mechanical fluctuations. But you see, that is second order in your path variable, in your positions and momentum. This is just a sketch. I'm not writing a rigorously correct, formally correct equation, but it's eta squared. Eta squared is just like your position and the moment and the velocity. So that second correction contains the second power of the velocity and the second power of the position. Now that is just a harmonic oscillator. The solution of the harmonic oscillator we already know. Or the path integral of the harmonic oscillator we already know. So you can just even calculate the first order correction to the classical approach. So you don't need to solve the Schrödinger equation. What you need to do is just solve the classical action. And then you have an approximation for the quantum mechanical problem. In fact, if you calculate the classical action for the free particle, this is exactly what you get. You exactly get that exponential. You can do the same thing, same treatment. Well, we will not do it, don't worry. about the harmonic oscillator, you can calculate it by just following this procedure, more or less. It will be a bit more technical, but kind of straightforward. You will obtain a final expression, which will be a prefactor multiplying an exponential, and that exponential will be exactly the classical action of the harmonic oscillator. So at least for the harmonic oscillator, this approximation basically gives you an exact result. So solve the classical problem, you know the solution of the quantum mechanical problem. And even for non-harmonic oscillators, non-harmonic systems, this will give you most of the time quite a good approximation. Of course, you still need to solve the classical problem. But that solution, if you know that solution, you don't need to go and solve the Schrödinger equation. You already have an approximate solution of the Schrödinger equation. But it's also expected from our previous discussions. Remember when we said that let's just write psi as square root of rho, which was the probability density, e to power I over h bar times s. And at lowest order in h bar, s was approximately s classical. So it's not a really big surprise. You can prove that the classical solution gives you an approximate wave function, either using wave functions or just using path integrals. Whichever one you prefer. Basically, they are equivalent. They are the same description of the same thing. They contain exactly the same information. It's just in one of them, it will be easier to see some properties. It will be easier to see those same properties in the other approach, some other properties in the other approach. So it's just kind of a personal taste. Okay, any questions? Okay, let's give a 10 minutes break, and then we will continue with other things.